6.2 Volumes by cross sections. We are going to use calculus to find the volumes of three-dimensional shapes where the cross sections are geometric shapes like squares, triangles, semicircles, rectangles, and things like that. Finding the formula for the area of the cross section is the tricky part, but once you've figured that out, then just integrate like you've been doing. So in general, if the cross sections are perpendicular to the x-axis, solve the equations for y. If the cross sections are perpendicular to the y-axis, solve the equations for x. So for cross sections of area A of x, taken perpendicular to an axis, the cross sections taken perpendicular to the x-axis, you have the volume equal to the integral from a to b of a of x dx. Cross sections taken perpendicular to the y-axis, you've got the volume is the integral from c to d, a of y dy. So now, do you recall the area formulas from geometry? And so if I called each of these sides of the square x, our a of x is going to be x squared. Here, if these are equilateral triangles, and that means that all the sides are x, and I know that the area of a triangle is 1/2 base times height, I would need to know the height. And when I drop that perpendicular, this right here would be 1/2 x, and I would use the Pythagorean theorem. My hypotenuse squared is equal to my side squared plus my side squared. I'm actually solving, forgot my plus. I'm actually solving for h here in terms of x. So I'm going to subtract 1/4 x squared from both sides. Now, this is a 1x squared, so I'm going to make it 4/4 x squared. So this becomes 3/4 x squared equals h squared. And then you take the square root, leaving me with the square root of 3 over the square root of 4, which is 2, and the square root of x squared, which is x. So that's my height. So if I was going to do my area, it's 1/2. My base is x times my height, square root of 3 over 2x, and then I would simplify square root of 3 over 4, x squared would be my a of x for that equilateral triangle. Isosceles right triangle. Okay, so for this one, this would be your base, and this would be your height. But on an isosceles right triangle, it has to have at least 2 pairs of equal sides. So I know that my 2 pairs of equal sides are those 2 legs. And so since they are my base and my height for an isosceles right, it would be 1/2 x times x, which would be x squared over 2. And then a semicircle. And remember, your semicircle would have r here and r here. And if we were finding the area of a whole circle, it'd be pi r squared. So this is going to be 1/2 pi r squared. So this is what these cross sections look like on the next page here. And you can see that there is a base that is, some sort of piece of a function, or it might be the intersection of 2 functions. And then coming up from that are different shapes. So for the first one, you've got squares, and for the second one, you have semicircles. And so you can imagine if these were just infinitely many of those, what that figure would end up looking like. So we're going to kind of dissect it here and start going through what these, they're kind of leading you into what you would do when you're finding the volume of the whole thing. So first, we're going to write the area of one square in terms of the given functions. So for this one, the area of the square is going to be, side times side. So basically, if we know it's a square and that they're both the same, it's just going to be that. Area is f of x minus g of x quantity squared. By adding an infinite number of squares, the total of the cross-sectional areas would give us the volume of the solid created. So write this volume on the interval AB as an integral. So if I was going to find my volume, it would be the integral from A to B of my A of x, which is my f of x minus g of x quantity squared, dx. Okay, so that would be my volume, because you're imagining that you've got infinitely many of these. Okay, on the semicircle cross section, semicircles are a little tricky. In this case, you need to find the radius in terms of the functions. Then write the area for one semicircle cross section. So if you were writing the area here, A of x, for one of these semicircles, so we know it's going to be 1/2 pi r squared, but how would I get r if I know this whole thing is f of x minus g of x? I would have to take f of x minus g of x and divide it by 2 and then square it. That would be my r. So my radius for this semicircle is half of this. And so when I square that 2, I get 4, and I multiply it by this 2 in front, I get 8. This gives me pi over 8 times f of x minus g of x squared. So that is my area. And now write the volume of this solid generated by slicing the region between the curves f of x and g of x on the interval AB. So my volume is going to be the integral from A to B, pi over 8 times f of x minus g of x squared dx. And we know that that pi over 8 is a constant, and so you can bring that out front so that you don't have to worry about that being in the integral and, you know, crowding things up where you could not, where you'd have trouble finding that integral. Okay, so good job. Now look at this isosceles right triangle cross section. So these are isosceles right triangles coming up out of the page. Their base is that f of x and g of x cross, well, not cross section, but base is that f of x minus g of x area. So write the area of the triangle. So you're writing the area of that triangle in terms of f of x and g of x. And so I'm going to go back and show you a couple things, but they've given you this picture here. And so your area is going to be 1/2 base times height. And so that gives you f of x minus g of x quantity squared over 2 for your a of x. And write the volume of this solid generated as an integral in terms of f of x and g of x on the interval from a to b. So my volume is the integral from a to b, 1/2 f of x minus g of x squared. And that would be dx. And you could bring that 1/2 out in front so that you could only need to focus on the f of x minus g of x squared in your integral. Okay? And so now, what about equilateral triangle cross sections? And so they've already drawn it here. They've told you what this base is here. But we know that all of these, since it's an equilateral triangle, they're all the same. And so if I drop a perpendicular and call that H, this is going to be f of x minus g of x divided by 2. That base just from here to here, right? Just that base of that right-sided right triangle. And so we could say that the hypotenuse squared is equal to side squared plus over 2 squared. And so now this is just going to stay f of x minus g of x squared, and this is going to become 1/4 f of x minus g of x squared. So here we're going to subtract 1/4 f of x minus g of x squared on both sides, because you can think of this f of x minus g of x squared as like terms here. Like, again, this is 4/4, and so this becomes 3/4 f of x minus g of x quantity squared equals h squared, and then take that square root. So square root of 3 over 2 times f of x minus g of x is my h. So now, once I have my h, I can write my area, and it's going to be 1/2. My base is f of x minus g of x, right? Because my base is going to be this whole thing, which is this, and then times my height, which is the square root of 3 over 2, f of x minus g of x. And then to simplify that, we would have square root of 3 over 4 f of x minus g of x squared. Okay, so that would be my area. And then use calculus to write the volume of the solid generated by summing the areas of the infinite number of triangles on the interval AB. So our volume is the integral from A to B, and our A of x is square root of 3 over 4 f of x minus g of x squared dx. And so we would probably bring that square root of 3 over 4 out front, integral from A to B, f of x minus g of x squared dx. Okay, so just to kind of take you back up here for a minute to look at this and how we figured it out. So on the cross sections here, you know, they were trying to figure out what this right here was, and they realized that, oh, that's just going to be the y value of this function, because remember, this is like an x comma f of x point, and the y value of this function, where this is kind of like an fx comma g of x value. And if I wanted to find what this distance here is, let's call it d, that distance is going to be the top y value minus the bottom y value. And if this is a, square, then that's how they got this right here. And for this one, if you look, you've got the same thing going on, that the base of your semicircle ends up being f of x minus g of x, just like they did here. This was the base of our semicircle. And so to find the radius, we had to divide by 2. And so I just wanted to point out, because you're going to have to find these. So you saw this right here was f of x minus g of x. It's a right isosceles triangle, so you knew that this was also f of x minus g of x. This one is equilateral triangle, so this is f of x minus g of x. That meant that this was f of x minus g of x, and this was f of x minus g of x. So, they drew these things for us, but you're going to have to do that in the future. So I want to make sure that you are thinking like that. And we're going to do some examples that will help you think like that. So example number 1, find the volume of the solid whose base is bounded by the function y equals the square root of x equals 4, and the x-axis. Okay, so we're going to sketch a graph of this. We've got, I think I'm going to do it in blue. We've got, there's my square root of x. Here's my x equals 4. and here's my x-axis. So they're talking about this being the base of your solid. Okay, that is the base of your solid. Your cross section is a square perpendicular to the x-axis. So now I'm going to do this in a different color. I don't know, what color should I use? I guess pink. So I'm perpendicular to the x-axis, and I'm coming up out of the page a square, you know, so it's going to be wider here just because, but you're imagining all these squares just coming up out of the page, each one of them, the distance, you know, the distance along the bottom of the square, or its side length, is actually the same. Think of this as an x comma square root of x point. This would be also an x comma square root of x point. And think that, okay, for this point, that's your x, and this is your square root of x. And for the next one, this is your x, you know, this is your square root of x. So, you know, these squares are dependent upon where they are located on this base. And what we're going to do is when we find the volume, we're basically just taking all of these and adding them up, infinitely many, from 0 to 4, okay? So from 0 to 4, our volume. And we're going to say that this is square root of x squared. That's our a of x. You know, what is the area of your square, of any one square? It's the square root of x squared. So what we're going to end up doing is those are going to cancel. This is just going to be the integral from 0 to 4 x dx. So that's going to be 1/2 x squared from 0 to 4. And so 1/2 times 4 squared minus 1/2 times 0 squared is going to be 8. And I know that this is volume, so I'm just going to say units cubed. You won't always see that everywhere, but I like to remind myself that I'm finding a volume. And then example number 2. Find the volume of the solid whose base is a region bounded by the circle x squared plus y squared equals 9, with cross sections taken perpendicular to the x-axis. So I'm just going to draw a circle here, centered at 0, 0. Of course, this is 3, and this is 3. This is -3. This is -3. They're perpendicular to the x-axis, and they're right isosceles triangles. So I'm going to choose yellow for this one. Think about it. Perpendicular to the x-axis, and they're right isosceles triangles. Oh, with the hypotenuse lying on the base of the circle. So this right here that I just drew right here is your, I'm going to erase this piece. It took everything. Sorry. Let me draw that again. But that piece is the hypotenuse. So you have to be careful with this one. If the base, it says perpendicular to the x-axis are isosceles right triangles with the hypotenuse lying on the base of the circle. So that means that this is coming up as your right angle here. And so you need to think about how you are going to solve this. I'm going to stop the video at this point because I'm getting ready to have